Hi everyone, today we'll see about the first perspective of cognitive radio architecture, which includes functions, components and design rules of cognitive radio. This video is posted on the request of our viewer Lokesh Kundaruthi. Let's get into today's topic. Architecture is a comprehensive, consistent set of design rules by which a specified set of components achieve a specified set of functions in products and services that evolve through multiple design points over time. This section introduces fundamental design rules by which a software-defined radio, sensors, perception and automated machine learning may be integrated to create an aware, adaptive cognitive radio. Further, each of the different aspects of cognitive radio architecture contribute to government, academic and industry dialogue. The SDR components and the related cognitive components of cognitive radio appear in this figure. We know that cognitive radio architecture articulates functions, components and design rules of next generation standalone and embedded wireless devices and networks. This figure clearly shows different modules of cognitive radio, which are hardware, software and cognition. First comes the hardware platform with RF access and computational resources. It further includes antenna, modem, information security, baseband and user interface. Next is the software module, which includes baseband modem, backend control and equalizer algorithm. These SDR architectures are defined in Unified Modeling Language Object Models and CORBA, that is Common Object Request Broker Architecture, Interface Design Language and XML descriptions of the UML models. Last comes the cognition, which describes the SDR in RXML, that is Radio Extensible Markup Language. We know that RXML intelligence includes a priori radio background and user stereotypes as well as knowledge of radio frequency and space-time, which is perceived and experienced. This includes structured reasoning with cognitive radio peers and cognitive wireless networks and ad hoc reasoning with the users, that is learning from experience. A simple cognitive radio architecture includes the functional components as shown in this figure. A functional component is a black box to which functions have been allocated but for which implementation has not been specified. At the level of abstraction of this figure, the components are functional but not physical. Let us get into the details of these functional components. First is the user interface, which goes well beyond buttons and displays. The traditional user interface has been partitioned into substantial user sensory subsystem and a set of local effectors. The user sensory interface includes buttons, that is the haptic interface, and microphones, that is the audio interface, to include acoustic sensing, that is directional, which is capable of handling multiple speakers simultaneously, and also able to include full motion video with visual scene perception. In addition to this, the audio subsystem does not just encode the audio for transmission. It also parses and interprets the audio from designated speakers, such as the user, for a high-performance spoken natural language interface. Similarly, the text subsystem parses and interprets the language to track the user's information states, detecting plans and potential communications and information needs. Thus, the local effectors synthesize speech along with traditional text, graphics and multimedia displays. Next, the system apps are the information services that define value for the user. Historically, voice communications with the phone book, text messaging and exchange of images or video clips comprised the core value proposition of system apps for SDR. Next, the cognition components, which provides all the cognition functions, starting from the semantic grounding of entities in the perception system to the control of the overall system through the planning and initiating actions, that is, learning user preferences and RF situations in the process. Each of these subsystems contains its own processing, local memory, integral power conversion, built-in test and related technical features. In cognitive radio architecture, the design rules may include a list of quantities and type of components, as well as the interfaces among those components. The table shown here addresses about the internal interfaces among the 6 functional components. That is, it shows how each and every single functional component is interrelated with the other functional components. In this, the letter P indicates primary, A indicates afferent, that is carrying inward, E indicates efferent, that is carrying outward, C indicates control, that is how it influences, M indicates multimedia, D indicates data, and S indicates secondary. Other than this, the boxes which are not designated with P or S or A or C or any other letter are called ancillary. That is, it provides the necessary support needed. Further, we know that the commercial wireless community led by the cell phone giants like Motorola, Ericsson, Nokia and others envision a much simpler architecture for mobile wireless devices consisting of two APIs, that is application programming interfaces, one for the service provider and another for the network operator. Here, the Information Services API includes the interfaces from numbers 13 to 18, 21, 27 and 33. While the Cognition API includes the interfaces 5, 11, 17, 23, 25 to 30, 29 and 35. The tables given here are self-expressive. This particular table shows the internal interfaces between the 6 functional components and the user sensory perception. Have a look on this. The next table shows the interface between the functional components and the environment. This table shows the interfaces between the functional components and the system applications. The next table shows the interface between the functional components and the SDR. This table shows the interface between the functional components and cognition. This last table shows the interface between the 6 functional components and the effector component. We know that these interface changes enable the cognitive radio to sense the situation represented in the environment, to interact with the user and to access the radio networks on behalf of the user in a situation-aware way. This section suggests additional design rules by which user domains, sensory domains and RF band knowledge may be integrated into industrial strength aware adaptive cognitive radio products and systems. The following design rules further circumscribe the way in which the cognitive radio functions are mapped to the components of wireless personal digital assistance, that is WPDA, within the envisioned architecture as follows. First, the cognition function shall maintain an explicit topological model of the world, of the environment, including the user, physical environment, radio networks, and the internal states of the radio. Here, context shall be axiomatically represented using the topological model. Next, the model of the world shall follow an explicit axiomatic treatment of time, space, radio frequency, radio propagation, and the identity of entities. Next, the models shall be represented in an open architecture radio knowledge representation language, that is RKRL, which is suited to the representation of radio knowledge. This language shall support topological properties and axiomatic models of cognitive radio. Next, the cognition functions can maintain location awareness, which includes sensing of the location through GPS and sensing position from local wireless sensors and networks. Here, location shall be an element of context. Next, the cognition functions shall maintain awareness of time to the accuracy necessary to support the control of radio functions. In this case, time shall be an element of context. Next, the cognition functions shall maintain an awareness of the identity of the PDA, of its primary user and of the other legitimate users designated by the primary user. Here, current user shall be an element of context. Next, the cognition functions shall reliably infer the user's communications context and apply that knowledge to the provisioning of wireless access by the SDR functions. The cognition functions can model the propagation of its own radio signals with sufficient fidelity to estimate the interference to other spectrum users. The cognition function assures that interference is within the limits specified by the spectrum use protocols in effect in its location, that is in spectrum rental protocols. It shall defer to the wireless network in contexts where the network manages interference. Next, the cognition functions can model the domain of applications running on the host platform, sufficient to infer the parameters needed to support the application. Parameters modeled include quality of service, data rate, probability of link closure, that is grade of service, and space-time context domain within which wireless support is needed. Next, the cognition functions shall configure and manage the SDR assets to include hardware resources, software personalities, and functional capabilities as a function of network constraints and use context. Next, the cognition functions also administer the computational resources of the platform. The management of software radio resources may be delegated to an appropriate SDR function. Constraints and parameters of those SDR assets shall be modeled by the cognition functions. The cognition function shall assure that the computational resources allocated to the applications, interfaces, cognition, and SDR functions are consistent with the user communication context. Further, cognition functions shall represent degree of belief in external stimuli and in inferences. A certainty calculus shall be employed consistently in reasoning about uncertain information. The cognition functions shall recognize preemptive actions taken by the network and the user. In case of conflict, the cognition functions shall defer the control of applications, interfaces, and SDR assets to the network or to the primary user according to an appropriate operation assurance protocol. We know that the functional architecture identifies components and interfaces for cognitive radios with sensory and perception capabilities in the user domain, not just the radio domain. The functional architecture and interfaces which we saw earlier do not assist the radio engineer in structuring knowledge, nor do they assist much in integrating machine learning into the system. Rather, the fine-grained architecture developed is derived from the functional requirements to fully develop the three core capabilities. They are radio knowledge, user knowledge, and the capacity to learn. A cognitive radio is an SDR with flexible, formal, semantics-based entity-to-entity messaging through RxML and integrated machine learning of itself, user, RF environment, and the situation. First comes the radio knowledge, which is a computationally accessible, structured technical knowledge about radio. RxML is the primary enabler and product of this foray into formalization of radio knowledge. The software communication architecture structures the technical knowledge of the radio components into unified modeling language and XML. RxML will enable the structuring of sufficient RF and user world knowledge to build advanced wireless enabled or enhanced information services. Thus, software radio architecture and software communication architecture focus on building radios, while RxML focuses on using radios. In addition, AACR is a multi-band, multi-mode radio, that is MBMMR. So, the knowledge must be comprehensive, addressing the majority of radio bands and modes available to an MBMMR. This knowledge is formalized with precision that should be acceptable to standards like ETSI, ITU, and other regulatory authorities. The capabilities required to be a cognitive entity are to sense, perceive, orient, plan, decide, act, and learn. The table shown here is illustrative and not comprehensive, but it characterizes the technical issues that drive an information-oriented AACR node architecture. Next comes the user knowledge, which is formalized with a degree of detail relevant to the information services that is necessary to give the cognitive radio the ability to acquire from its owner and other designated users in an incremental manner. This incremental knowledge acquisition was motivated with the introduction to machine learning. These machines recognize the opportunities for learning through joint probability statistics like histogram. The effective use cases clearly identify the classes of user and the specific knowledge learned to customize the envisioned services. This is defined in user knowledge in architecture. The knowledge about the radio and about the user needs for wireless services must be expressed internally in a consistent form, so that the information services relationship may be autonomously discovered and maintained by the self on behalf of user. There are specific methods of cross-domain grounding. First, RF to user shaping dialogue to express precise RF concepts to non-expert users in an intuitive way. Next, RF to user learning jargon to express RF connectivity opportunities in user. Last, user to RF relating values to actions, which relate user expression of values to features of situations that are computable and that relate directly to RF domain decisions. This figure clearly shows the relationship among user and RF domains. The steps 4, 5 and 6 in this figure all benefit from agreement across domains on how to refer to radio services. Optimizing behavior to best support the user request, continually adapting the user with repeated regrounding of terms in the user domain to conceptual primitives and actions in the RF domain. Both commercial and military information services entail cross-domain grounding. The cognition component must be able to access, manage and control all of its own resources, including validating downloads. Self-referential inconsistency is well known in theory of computing to be a potential black hole for computational resources. Specifically, any Turing-capable computational entity that reasons about itself can encounter unexpected Gödel-Turing situations from which it cannot recover. Thus, Turing-capable systems are known to be partial, where the computing procedure will never terminate. To avoid this paradox, cognitive radio architecture mandates the use of only total functions, typically restricted to bounded minimalization. Watchdog step counting functions or timers must be in place in all its self-referential reasoning and radio functions. A watchdog timer is a hardware timer that automatically generates a system reset if the main program neglects to periodically service it. It is often used to automatically reset an embedding device that hangs because of a software or hardware malfunction or fault. Without the reliable watchdog timer and architecture, and without this proof to establish the rules for acceptable computing constructs on cognitive radios, engineers and programmers would build cognitive radio that would crash in unpredictable ways, as their adaptation algorithm gets trapped in unpredictable, unbounded self-referential loops. The functions of the architecture shown in this table are not different from those of the 6-component architecture which we saw earlier. But this represents varying degrees of architecture instantiation of the 6 components. Coming to degrees of architecture instantiations, first comes cognition functions of radio, which entail monitoring and structuring knowledge of behavioral patterns of itself, user and environment to provide information services, learning from experience to tailor services to user preferences and differing radio environments. Next is adaptation functions of radio that responds to a changing environment but can be achieved without learning if the adaptation is pre-programmed. Next is awareness function of radio, which extracts usable information from a sensor domain. Awareness stops short of perception. Awareness is required for adaptation, but awareness does not guarantee adaptation. For example, embedding a GPS receiver into a cell phone makes the phone more location aware. But unless the value of the current location is actually used by the phone to do something that is location dependent, the phone is not location adaptive, only location aware. These functions are a subset of cognitive radio architecture that enable adaptation. Next is perception functions of the radio. This continuously identify and track knowns, unknowns and backgrounds in a given sensor domain. Backgrounds are subset of a sensor domain that share common features that entail no particular relevance to the functions of the radio. These functions are a subset of cognitive radio architecture that enable cognition. Last is sensory functions of radio that entail those hardware and software capabilities that enable a radio to measure features of a sensory domain. Sensory domains include anything that can be sensed, such as audio, video, vibration, temperature, time, power, fuel level, ambient light level, sun angle, barometric pressure, smell, and anything else which is imaginable. Sensory domains for vehicular radios may be much richer than those of the wearable radios. Sensory domains for fixed infrastructure could include weather features like ultraviolet sunlight, wind direction and speed, humidity, traffic flow rate or rain rate. These functions are a subset of cognitive radio architecture that enable perception. Thank you for watching this video. If you find this video to be useful, kindly subscribe it and share it with your friends. And don't forget to click that like button because it will motivate me to post more videos. If you want me to analyze any other topic, kindly let me know in the comment section. Thank you once again.